So in the previous module, we talked a little bit about the mathematical details behind dynamic causal modeling, or DCM. In this module, we're going to do the same thing for Granger causality. So Granger causality is a technique that was originally developed in the econometrics literature, but has recently been applied to neuroimaging as well. And so Granger causality is a little bit different from dynamic causal models, and it doesn't rely on an a priori specification of a structural model, but rather it's an approach for quantifying the usefulness of past values from various brain regions in predicting current values in other regions. So now let's let x and y be two time courses of length t extracted from two separate brain regions. Now, each time course can be modeled using a linear autoregressive model of the mth order. So here, for example, we say that x of n, so this is the value of x at time n, depends on the past m values through this sort of linear equation. So we have a1 is the weight for the value of x at time n minus 1, a2 would be the weight for x at time n minus 2, etc. And then we have an error term, epsilon, as well. Similarly, we model y doing its m past values as well. So this is what's called an autoregressive model of the mth order. So basically, all we're doing here is we're modeling the x at a certain time point using its past values. Here, epsilon x and epsilon y are both white noise. We can just assume for simplicity that they're IID normal errors. The next step in Granger causality is to expand each model using the autoregressive terms from the other signal. So basically, we still use the past m values of x in modeling the current value of x, but we also use the past m values of y. And then similarly, we do that for y. We use both the past n values of y and the past m values of x. Okay? So now the current value depends both on the past m values of its own time course, but also the past m values of the other time course. Okay, so now we have four equations here. We have x, how x depends on its own past, how y depends on its own past, how x depends on its own past and the past of y, and how y depends on its own past and the past of x. So using these models, we can test whether the history of x has any predictive value on the current value of y and vice versa. And so if the model fit is significantly improved by the inclusion of these cross-autoregressive terms, then this provides evidence that the history of one of the time courses can be used to predict the current value of the other. And so we infer what's called a Granger causal relationship between the two. So how do we measure this? Well, Goecki proposed a measure of linear dependence, fxy, between the two time courses x and y, which implements Granger causality in terms of vector autoregressive models. So here, f of xy is a measure of the total linear dependence between x of y. If nothing about the current value of x can be explained by a model containing all the values of y, then f of xy will be equal to 0. And similarly, we can say that if nothing about the current value of y can be explained by a model containing all the values of x, then f of xy is 0. So the term f of xy can be decomposed into the sum of three different components. We have f of xy is equal to f of x to y plus f of y to x plus f of xy, the dot product here. So f of x to y and f of y to x are measures of the linear directed influence from x to y and y to x, respectively. So if past values of x improve the prediction of current value of y, then f of x to y is greater than 0. A similar interpretation holds for f of y to x. The term f x dot y is a measure of the undirected instantaneous influence between the two series, the improvement in the prediction of the current value of x by including the current value of y in a linear model already containing the past values of x and y. So how do we compute these three different components? Well, this is what Goecki proposed, and basically using these vector autoregressive models. So here we have a lot of equations here, but the key thing here that I just want to show you these equations. We don't have to dig in too deep into them, but basically what we have is we have different variance components here. So if we have a model of x that just depends on the past values of x, then we have a variance component sigma of 1. Similarly, for y, that depends only on its own past value, we have a covariance matrix T1. Now, if we start including the other terms into it, we get this equation Q, and now the variance-covariance matrix changes a little bit. So we have sigma 2, which is the variance-covariance matrix of x when we include both past values of x and y, and T2 is similarly the variance-covariance matrix of the y when we're including past values of both x and y. So using these variance components, the total linear dependence between x and y can be written in the following way. So again, f of x and y is equal to f of x2y plus f of y2x plus f of x dot y. And each of these terms can be expressed in terms of the variance components from the previous model. So for example, if we're looking at f of x2y, this is the natural logarithm of the determinants of t1 divided by the determinant of t2. Now, what's the difference? What does this represent? Well, T1 is the variance component when we only have y in the model. So we say that the current value of y only depends on past values of y. T2 is when we also include x. So if x explains a lot about y, then T2 should actually be much smaller than T1. And so f of xy should increase and become bigger. So that's the general idea behind these equations. And if you're mathematically interested in these equations, you can dig in further into them. But I just want to give you a brief taste of what they look like. So if past values of x improve on the prediction of the current value of y, then the idea here is that f of x to y should be large. A similar interpretation, but in the opposite direction, holds for f of y to x. And so the difference between these two terms can be used to infer which region's history is more influential on the other, and this difference is referred to as Granger causality. A Granger causal map is computed with respect to a single selected reference region, such as a seed region. So this is very similar to seed analysis that we talked about in functional connectivity. But here we basically take a seed region, and we take a time course from that seed region, we call that x. Then we let every other voxel in the brain be the y that we test the Granger causal relationship to x. So basically it's sort of like a Granger causal seed analysis. And so it maps both sources of influence to the reference region and targets of influence from the reference region over the whole brain. Here's an example from work by Robrook showing regions that where where the reference to voxel is bigger than the voxel to reference, and vice versa. The reference region, or the seed region, is the region shown in the crosshairs here. So just to end with a few brief comments, from the definition of Granger causality, it's clear that the idea of temporal precedence is used to identify the direction and strength of causality using information in the data. So if the past of y explains a lot about the current value of x, then we infer this Granger causal relationship. And so this is all about temporal precedence. So while it's reasonable that temporal precedence is a necessary condition for causation, it's really not a sufficient condition. So there's things that happen before another event, but that doesn't mean that that event caused the other event. So therefore, to directly equate Granger causality and causality as most people mean it requires a bit of a leap of faith. We'll talk about this a little bit more in the next module. Okay, so that's the end of this module. Both this module and the previous one on DCM were a little bit more mathematical. I just wanted to give you a little bit of a look under the hood, how these methods work. Okay, the next module will finish up talking about effective connectivity. I'll see you then.